So, you ever wonder how giants like Netflix or Twitter just work? I mean, what kind of digital magic is holding those things up? Well, today, we're going to pull back the curtain on that invisible architecture, the stuff that powers billions of clicks, posts, and streams every single day. Let's dive in.
Now, really, think about it. The season finale of some huge show drops, or there's a massive global news story. Millions of us are hitting refresh at the exact same second. So why doesn't the whole internet just, fall over? It really does feel like magic, but it's not. It's actually something way, way cleverer.
And that secret? Well, it has a name: system design. You can think of it as the blueprint for building these digital fortresses, these massive, resilient systems that can handle pretty much anything we throw at them. And today, we're going to walk through the core ideas that make it all happen.
So what's the best way to get our heads around this? Well, I think it's by telling a story. We're going to follow the journey of a simple little app as it just explodes into a global phenomenon, and we'll see all the engineering hurdles it has to clear along the way.
All right, so imagine this. You've got a brilliant idea for an app. You code it up on your laptop, and for you, user number one, it's absolutely flawless. The code is clean, every click is lightning fast. It's perfect.
But then, the best and kind of the worst thing happens. Your app starts to get popular. I mean, really popular. And all of a sudden, that success starts to look a whole lot like a major problem.
And then the messages start rolling in. At first, it's just a trickle, but then it's a flood. Hey, why is this so slow? The app just crashed on me, again. That very same code that worked so perfectly for just you is now failing for thousands. Your amazing app is literally drowning in its own success.
So this brings us right to the heart of the matter, right? What is the real difference between an app that's fast for one person and one that's fast for millions of people all trying to use it at the same time?
And the answer to that question highlights this super important distinction: performance versus scalability. See, a performance problem means your app is just slow, period, even for one person. But a scalability problem, that's what our app has. It's fast for one user, but it just completely buckles under heavy load. That's the specific problem we have to solve.
Okay, so how on earth do engineers fix this kind of massive digital traffic jam? Well, they turn to a very specific toolkit, a set of strategies designed to help systems like ours scale up.
So, here's our simple three-step plan to fix this thing. First, we're going to get ourselves a traffic cop. Second, we're going to add more lanes to the highway. And third, we'll create some really clever shortcuts to help ease all that congestion.
All right, step one, the traffic cop. In the engineering world, this is called a load balancer. I want you to imagine a host at a super busy restaurant. Instead of sending every single guest to the same poor, overworked waiter, they spread everyone out evenly across all the available tables. A load balancer does the exact same thing for user requests. It makes sure no single server gets overwhelmed.
Step 2 is all about adding more servers. This is a concept called horizontal scaling. Now, instead of trying to build one giant, super powerful server, which gets really expensive and has its limits, you just add more standard, cheaper machines to the mix. It's just like adding more tables to your restaurant instead of trying to build one ridiculously enormous table.
And finally, step 3, we create shortcuts with something called caching. Think of it like this. Instead of running down to your basement pantry every single time you need a pinch of salt, you just keep a little bowl of it right next to the stove. That's what a cache does. It stores frequently accessed data, like a celebrity's profile page, in a super fast, easy-to-reach spot, so the system doesn't have to bother the main database for it every single time.
Okay, great. We've solved the traffic jam. Our app is fast again. But in fixing that problem, we've uncovered a brand new one. And honestly, this one is much, much bigger. With millions of users comes this unbelievable tidal wave of data.
I'm talking about terabytes, maybe even petabytes of information. All those photos, all those posts, all those messages. Our single little database, which was totally fine at the beginning, just can't handle it anymore. It has officially become the new bottleneck in our system.
So this brings engineers to a really fundamental choice they have to make: SQL versus NoSQL. You see, SQL databases are amazing for structured, predictable data. Think of a banking system where every single transaction has to be perfectly consistent. NoSQL, on the other hand, is built for massive scale and flexibility, which is perfect for the kind of messy, semi-structured data you get from a social media app.
And the toolkit for managing all this data gets even more sophisticated from there. Engineers use techniques like replication. You can think of that as just photocopying your database so more people can read from it at once. Or sharding, which is like tearing a giant phone book into smaller, more manageable volumes, like A through F, G through M, and so on. Each of these is a specialized tool for a very specific kind of data problem.
You know, all of this, the load balancers, the databases, the caching, it all leads us to the single most important lesson in all of system design. And it's this: there are no easy answers. There are no perfect solutions. There are only trade-offs. Seriously, this is the mantra of every single system architect out there. Everything is a trade-off. Every decision you make, whether it's choosing a database or adding a cache, it improves one thing at the expense of something else. Maybe you get faster reads, but now your writes are slower. Maybe you add more features, but now the whole system is more complex. And the ultimate example of this whole dilemma is the famous CAP theorem. It's a fundamental law of distributed systems. It basically says that in any system that runs on more than one computer, you can only pick two out of these three guarantees: consistency, availability, or partition tolerance. You literally cannot have all three at the same time.
But here's the really crucial insight. Because networks in the real world are unreliable. You know, cables get cut, servers go down. Failures will happen. So partition tolerance isn't really a choice. You have to design your system assuming parts of it will get disconnected. That means the real and often painful decision every architect has to make is choosing between consistency and availability.
So let's break that down. A system that chooses consistency over availability, think of a bank, will always show you the most up-to-the-second correct data. Or it will just give you an error. It refuses to show you stale information. But a system that chooses availability, like a social media feed, will always give you some kind of response, even if the light count you're seeing is a few seconds out of date. It prioritizes always being online over being perfectly, instantly consistent.
And that's really the heart of it all. There's no such thing as a perfect system. Great system design isn't about finding some magical one-size-fits-all solution. It's about deeply understanding these trade-offs and making smart, deliberate choices about what matters most for the users you're building for.
So the next time your favorite app feels a little slow, or maybe a feature isn't available for a minute, just pause and ask yourself, is that a mistake? Or is it actually the result of a deliberate, incredibly difficult design choice that was made specifically so that millions of other people can keep using that same service right alongside you?